Hello everyone, welcome back to my organic chemistry mini lecture. Today our topic will be imine and enamine. Imine and enamine are actually very common structures, intermediates in organic synthesis, and very useful. And today we will talk about both of them and how to make them and the hydrolysis of these two common compounds. And first, we will talk about how to make imine. So if you look at the example shown here, I have aldehyde. This is ethanol. And the other one is a primary amine. It's ethylamine. And this acid is the catalyst. And the product is called imine. So look at the structure of imine. It's actually carbon-nitrogen double bond in this compound. So this is acid catalyzed. It's actually a type of a condensation reaction between the carbonyl and primary amine. And I use the example of aldehyde, but actually ketone works same way. Okay, you can use ketone and also form imine. Let's look at the arrow pushing mechanism. First, we have the aldehyde here, the carbonyl compound, and the proton, that's the acid catalyst. First step is the protonation. So as usual, the lone pair of oxygen attack the proton, and that is the protonation. This way, the carbonyl functional group will be activated. So this carbon will be more electrophilic. And then the primary amine is the nucleophile, will attack this carbon, the lone pair on the nitrogen, push electron to this carbon, and then push the pi electron between the carbon oxygen here to oxygen. And then you form a nucleophilic addition product, intermediate. It's a tetrahedral intermediate. And then this oxygen will take this proton, push the sigma electron back to nitrogen. That's called a proton transfer. The intermediate will be another positively charged intermediate, and after proton transfer, the hydroxyl group will be activated and it will change to water as a much better leaving group. So next step is the lone pair on the nitrogen will push back to form a double bond here and then kick off the leaving group. Then that's elimination, formed this protonated imine as the intermediate. Last step is the base will deprotonate this proton, and the sigma electron push back to neutralize this positive charge. So final step is deprotonation, and the final product is the neutral compound, imine. Okay, so actually in this mechanism, all this arrow should be double arrow, so it means they actually are equilibrium. So it's reversible. If we add more water to this reaction, this imine actually will go back, so will decompose, or you can say hydrolysis happened, and they will go back to the carbonyl and imine. So I will talk about in slides here. So this is called hydrolysis. For this imine, you also need an acid as catalyst, and you need water. Okay, the product will be the carbonyl compound and the primary amine. In this example, the product is aldehyde and this primary amine. Let's look at the arrow pushing mechanism. You may notice that the arrow pushing it's similar with the last slides, just opposite direction. Okay, first step, you have a proton here, the acid, and this nitrogen will take the proton. It's a protonation, and then this way, this functional group, imine, will be activated. The carbon will be more electrophilic then. And then water will be the nucleophile. The lone pair of oxygen will attack this carbon and push the pi electron to the nitrogen to form this tetrahedral intermediate. And the next step will be the proton transfer. And the lone pair of nitrogen attack this proton and then push the electron of the sigma bond back to oxygen. And then you form this beta leaving group. So, and then this oxygen's lone pair will push back, kick up this beta leaving group. And this will be the byproduct here, the primary amine, the ethylamine. Then after this elimination step, you'll form this protonated aldehyde actually. So last step will be deprotonation. The base take this proton and push the sigma electron back to oxygen, and deprotonation step will give you another product, the ethanol, okay, the aldehyde. So this is a hydrolysis of imine. Now let's talk about enamine. This is example of the formation of enamine. So you may notice that this time I use a ketone as example. Again, aldehyde works the same way, and I use a cyclic ketone here. So if it's non-cyclic, it also works. Okay, now this is a secondary amine. Okay, so if you have a secondary amine react with a carbonyl compound, aldehyde or ketone, catalyzed by acid, you'll form enamine. Look at the structure of enamine. It's different with imine. Imine has a nitrogen-carbon double bond. In the enamine, no. So the carbon-nitrogen is a single bond, but there's a double bond between these two carbons. So that's called enamine. Why it's called enamine? En means alkene. This is alkene, and this is amine, so enamine. Now look at the arrow pushing mechanism of this reaction. First step, when you have a proton here, that's from the acid, this oxygen will take the proton, basically is activation of this carbonyl, the ketone. Protonation from this protonated ketone, and then this carbon will be more electrophilic. Then the secondary amine, this is ethyl-methylamine, will attack this carbon. That's a good nucleophile, and then push the pi electron to the oxygen to form this tetrahedral intermediate. That step is called a nucleophilic addition. Then proton transfer happen again. So the oxygen take the proton, push this sigma electron back to the nitrogen, and then this hydroxyl group will be activated, turns to a beta leaving group, water. And then the nitrogen's lone pair will push back to form the double bond and kick off this water as a leaving group. So this is elimination, and intermediate is similar with imine. Only difference, you have a positive charge here. So to get rid of this positive charge, we need to use a base, deprotonate this proton. We call this beta proton. Base, deprotonate the proton, the electron of the sigma bond push back to form a double bond here, and then push this pi electron to the nitrogen to neutralize the positive charge. So that is the deprotonation. Form last step, get the neutral product. It's called enamine. And this reaction is also reversible. It's in equilibrium. If you add more water to the equilibrium, actually the equilibrium will shift to left. Another way to say, this product will actually decompose back to the carbonyl compound and secondary amine. That's called hydrolysis. So for this reaction actually is type of reaction called condensation. Now look at the hydrolysis of the enamine under acidic condition. So you need acid and water, and then product will be the carbonyl compound and the secondary amine. Look at the first step. It's again protonation, actually you can see. But this time the protonation is not directly from the nitrogen attack the proton, is actually the lone pair of nitrogen pushed back to form a double bond here, and then the pi electron of this double bond will attack this proton. So it will form a positive charged intermediate. And then this intermediate will be attacked by water. So oxygen attack this nitrogen. Attack this carbon. And then pi electron will push to the nitrogen. Form this tetrahedral intermediate. And then, like usual, we have a proton transfer. This nitrogen attack this proton. And then push the sigma electron back to oxygen. And then this group will be turned to more activated leaving group. It's a better leaving group. And then this oxygen will use the lone pair pushback kick off the leaving group. So this step is called elimination. And this kicked off leaving group actually is this byproduct. This is ethyl methyl amine. And then this intermediate apparently need to be deprotonated to form a neutral product. So this proton will be deprotonated by a base, and the base will take the proton, push the sigma electron back to oxygen, and then after this deprotonation, you get this neutral ketone here. This is cyclohexanol. Okay, so this is the hydrolysis, the reversed reaction of this condensation. So if you have any questions, please let me know. Good luck.